I was in the organizing committee for this symposium a couple years ago, and I enjoyed it. I feel like I should summarize methods to study reaction mechanisms. Kinetics is just one method. Other methods include kinetic isotopic effect, operando, and in situ spectroscopies of various kinds like infrared. It also includes isotopic labeling and of course computational modeling. One method remains rare, although a very powerful tool, and that is a study of reaction intermediates. It is rare because not all of the reaction intermediates are stable enough to be studied, and not all can be isolated by trapping or somehow else, especially on surfaces. If you suspect an intermediate, you could study its behavior separately and see what happens. In such a way, a gas phase ketene was ruled out as an intermediate in the reaction that I'm going to be talking about today, and that is the decarboxylative ketonization. This reaction is used for the preparation of industrial ketones and as a step for the upgrading pyrolysis oil. The number of literature reviews on this subject appears in higher and higher frequency. Now it is every 2 years. Beta-keto acids, in square brackets, are intermediates of the recently most accepted mechanism for the preparation of ketones from carboxylic acids that proceeds with the decarboxylation. It is a very reactive and unstable molecule, even at room temperature. It has never been confirmed by operanda spectroscopy on catalyst surface. It has never been isolated by trapping. As we have learned now, its half-life is measured in microseconds at the reactor temperature. The goal for our study was to add keto acids on surface and study kinetics of its decarboxylation. In order to decarboxylate, beta-keto acid needs to be activated by adding electrophile to the oxygen atom of the beta-carbonyl group. In aqueous solutions, it happens through the protonation. On surface of metal oxides, it's the metal center to which the carbonyl group binds. We have chosen 4 beta-keto acids because they were proposed as intermediates in the cross-ketonization of a mixture of acetic acid A and isobutyric acid B. As part of the catalytic mechanism, the acid shown in red is enolized and it adds in the condensation step to the carboxyl group of the acid shown in blue. This makes 4 choices of beta-keto acids shown in square brackets, abbreviated by the 2 letters code BA, AB, AA, and BB. The first letter stays for the acid that was enolized, and the second letter for the acid that is the source of the beta-carbonyl group. During the decarboxylation step, the acid which was enolized is losing CO2. This has been verified in a number of isotopically labeled studies. We have synthesized those 4 beta-keto acids, and it was a remarkable achievement for the first time to obtain their molecular structure by single crystal X-ray diffraction. Beta-keto acids have been studied for more than a century, and up until 1960s it was not considered even possible to have them in a solid state. We have learned that beta-keto acids pack in the crystal by forming dimers through hydrogen bonding between carboxyl groups. In crystals, the carbonyl group is preserved from protonation because it is facing away from the carboxylic protons, which makes all crystals quite stable. We have kept them in the freezer for more than 3 years and nothing happens. However, when you take crystals out and expose to the atmosphere, any traces of moisture can destroy hydrogen bonding, and the crystal structure will be destroyed. In the melt, beta-keto acids decarboxylate quickly. We have carefully deposited beta-keto acids from dry ether solution on surface of monoclinic zirconia and NATase titania, untreated and treated with QAH. We have targeted less than a monolayer coverage. Prior to the deposition, metal oxides were calcined and cooled in a dry desiccator to exclude any moisture. After the contact of the catalyst powder with the ether solution, UV spectroscopy showed quick disappearance of beta-keto acid from the solution due to the absorption within 5 minutes. Ethyl ether was evaporated in a rotary evaporator at 0 degrees Celsius to preserve beta-keto acids from decomposition. In the infrared spectra, neat acids shown in red color have two bands, 1701 for the carboxyl group and then 1730 for the carbonyl group. After the deposition, the carboxyl group signals shift to the 1560, 1594 region, indicating formation of bidentate carboxylates. The beta-carbonyl group doesn't change much. It is in that region 1710, 1715, and the same pattern is observed for all acids on all catalysts. We may conclude that the major form of beta-keto acids, the absorption on surface, is through the bidentate carboxylate, shown on the left. The fact that the carbonyl group is not bound to the surface makes it stable against decarboxylation. When the carbonyl group binds to the surface, it makes the reactive form, which decarboxylate. DFT calculated values are in agreement with the experimental data. The rate of decarboxylation in solution and on surface of metal oxide was found by monitoring pressure in a sealed flask. An example of the original data is shown in here. Delta P is defined as the difference between the maximum pressure at the end of the experiment and the current pressure. A linear dependence of the ln delta P on time indicates first order reaction observed for all decarboxylation experiments, both in solution and on surface of metal oxides. When the rate constant is plotted as a function of temperature, a surprising fact is discovered, both in solution, top left diagram, and on surface of zirconia catalyst, top right and bottom left. You can see that the symmetrical ketones AA and BB, shown as red and blue graphs, are produced faster with zirconia catalyst compared to the unsymmetrical ketone from the acids BA and then AB, shown in purple and green. This is completely reversed with KH treated anatase titania catalyst. Bottom right picture, where the unsymmetrical ketones decarboxylates faster. The acids producing unsymmetrical ketones decarboxylate faster. You can see this trend better when the rate constant extrapolated to the temperatures of an industrial process. Symmetrical ketones produced faster with zirconia catalyst, while unsymmetrical ketones is produced faster with KH treated anatase titanium. This reactivity shown at 423 degrees Celsius for the beta-keto acid decarboxylation matches the cross-selectivity obtained with ZR and TK catalysts for the ketonization of acetic and isobutyric acid mixture. TK catalyst has been patented for its very selective production of non-symmetrical ketones. This fact has not been well understood. From the temperature dependence of the rate constant in coordinates ln k 1 over t, the activation energy and the enthalpy, free energy and entropy of activation have been calculated. The analysis of the rate constant for 4 different acids and catalysts leads to the conclusion that the entropy of activation is the major factor for the differences in the reactivity. The free energy of activation defines the rate constant. With zirconia catalyst, the free energy is lower and the rates are higher for the symmetrical ketones. With the KH treated titania catalyst, TK, this is the opposite. The free energy is lower and the rates are higher for the unsymmetrical ketones formation. The enthalpy has the opposite trend. It is not the enthalpy that defines the free energy. The entropy of activation is negative for all acids except for the acetoacetic acid, the least substituted AA, on the zirconia catalyst. If you compare top right diagram with the bottom left, you will see that the entropy has a high impact on the free energy. Graphs are almost mirror images of each other. Low negative entropy makes high values for free energy for unsymmetrical ketones, with zirconia and the picture is reversed with titania catalyst. We wanted to understand the strange effect of the product symmetry on the selectivity. Mass spectrometry analysis of the samples left after the decarboxylation showed presence of carboxylic acids on surface. Clearly, it must be a result of a retrocondensation reaction. With the rate constant K1, and we have found that it is only a minor direction, happening from 2 to 8%. And we propose that the retrocondensation is a reversible step, and it needs to be counted for the kinetic scheme. One of the kinetic schemes assumes reversible decarboxylation with a rate constant K2 and irreversible desorption of CO2 from the surface with a rate constant K3. We have tried to obtain the 5 rate constants shown on the scheme through the regression analysis fitting the experimental data. So we have obtained activation parameters, which we try to use to find the thermodynamic values by the difference between the activation parameters for the forward and reverse reaction to build the energy profile for the enthalpy, entropy, and free energy. Unfortunately, we have obtained a large margin of error in these calculations. However, we can still use this to see a trend which provides an insight into the reaction mechanism. First of all, the enthalpy and the entropy for the zirconium catalyst for the formation of symmetrical pairs in the retrocondensation product, like AA, this is a red line, compared to the unsymmetrical pairs is lower, and the graphs for the symmetrical ketones, they have a high level of energy and enthalpy and entropy. And so why is that? So we can think about this, and it's known that in the literature that the enolate of a small size acid like acetic acid can lay parallel to the surface because it can bind to the surface metal center by the negatively charged alpha carbon. This bond is shown as dotted line here. This is an additional stabilization which explains the low level of enthalpy for the species 1 when the enolized acid is the small acid A. For a larger size acid B, it would be more difficult to engage in such stabilization due to steric repulsion. Despite the low enthalpy, symmetrical species 1 AA have higher level of the free energy. That is because of their large negative entropy value. We proposed an explanation for the large entropy of unsymmetrical pairs because they might engage in the proton exchange shown on the bottom of this scheme. The enolate is a strong base which may deprotonate the neighboring carboxylate. Converted that carboxylate into the enolate. As a result, their role is switched, and those pairs may engage in the process of stealing the proton from each other several times before the condensation step can take place. Such variation increases the entropy, so that the free energy goes down for those unsymmetrical pairs. On anti-taste titania, analyzed species are oriented orthogonal to the surface, and the proton exchange is not discriminated there by the steric factor. So we take this case as a lesson for the careful use of DFT computation. A lot of times DFT calculation model only the straightforward path without paying attention to what else is possible there. In real systems there might be some other processes going in parallel which needs to be accounted for to improve the accuracy of the DFT modeling. So in conclusion, we found the first order reaction kinetics for the decarboxylation of beta-keto acids, and there was reversible retrocondensation because we've seen the carboxylates. And those carboxylates, one of them is enolized and they can steal proton from each other. They engage in that proton exchange, and that differentiates the catalytic activity on zirconia and TK catalysts. Those results explain high selectivity to symmetrical ketones with zirconia catalyst, and then high selectivity to unsymmetrical ketones with the TK catalyst for the cross-ketonization of a mixture of two carboxylic acids. This work was supported by NSF and by summer research program at St. John Fisher College. Thank you for your attention.